Hello and welcome to today's IWCS webinar. My name is Connie and I will be your Cisco WebEx producer for today's event. Now I'm pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we are pleased to welcome Paul van Zyl, Technical Manager for CBI Electric Telecom Cables, Brits, South Africa, who will be presenting his paper on the advantages of using reduced coating diameter optical fibers, 200 micrometers, in ADSS cables for deployment in FTTx networks. Paul van Zyl's tertiary studies earned him a diploma in electrical engineering, after which he joined Siemens Cables in South Africa in 1983. He worked alongside experienced cable design engineers contracted from Siemens in Neustadt, Germany, and was appointed cable design engineer in 1985. In 1986, he was appointed cable development engineer at ATC Limited, now CBI Electric Telecom Cables, where they manufactured mainly telecommunications cables, including fiber optics. His first major project at ATC was to investigate the pros and cons of different optical fiber cable designs to determine the company's future direction in this regard. In 1996, he was appointed as technical manager. Paul is currently the chairman of the South African Mirror Committee for IEC TC86 and SC86A, dealing with fiber optics. Paul, we welcome you to present at today's IWCS webinar series event. Please go ahead.
Thank you for the introduction, Ed, and I also want to acknowledge my co-author, Ian Davis, who worked with me to produce the paper. So the paper was originally presented at IWCS 2017 in Orlando, and also in March earlier this year at IWCS in Shanghai, China. The overview there reflects the main topics of the paper that I will be covering. But to start with, just a bit of background information. South Africa is located on the southern tip of Africa and is also called the Rainbow Nation due to its multicultural diversity. The total population is around 56 million people. The total distance across the country from north to south is approximately 2,000 kilometers or 1,300 miles. Compared to most other African countries, it's got relatively good infrastructure in terms of roads, railroads, and telecoms. It is the second largest economy in Africa after Nigeria. There are 9 provinces with main centers and their populations as listed in the table on your screen. South Africa is also one of the host countries to the largest radio telescope ever to be built, known as the Square Kilometer Array Telescope, or the SKA. Okay, the telecommunication networks in South Africa are fairly advanced. There are a number of submarine cable landing systems and various operators having long-haul and regional networks. The incumbent operator claims of having an optical fiber network comprising of more than 150,000 kilometers of cable. Even mobile operators that used to only lease capacity from fixed-line operators started building their own optical networks quite some time ago. The table on your screen there shows a community classification from a telecoms operator's perspective. Now, communities in South Africa vary from one extreme to another. For example, you can have a rather affluent suburb bordering onto an informal settlement. And, of course, for the business model to make sense, various technology solutions are deployed. There is also a tendency where you can have an upmarket gated community, for example, that would only prefer underground cable network installations, whereas aerial installations would suffice in most other communities. Some of the abbreviations there may not be known to everybody. So SMME stands for Small, Medium and Micro Enterprises, and SOHO stands for Small Office, Home Office. The country map there shows a distribution of income levels. To summarize this, it shows that less than 2% of the country's total area concentrates 50% of the population and 77% of national income. Now, during 2015, operators started competing in what we call a fiber land grab, where they sort of cherry-picked areas. They targeted areas where the anticipated connection rates were high and where cables can be installed quickly to deliver the largest possible network footprint. They have these technology maps on their websites showing available technologies, with fiber being a very attractive option. Now, the green area that you can see on the right, for example, shows DSL coverage, and below that FTTH for the same area. It is actually interesting to see how rapidly FTTH grew in recent times. The incumbent operator set itself a target in 2015 for 1 million homes connected by 2018, and there were a number of other operators setting themselves their own challenging targets at the time. The initial focus was pretty much on the number of homes passed, and this continued until the end of last year, when especially the incumbent operator realized that the actual connection rate wasn't as desired. The figures mentioned that it was only about around about 18%, which is very low, of course. So for now, there has been a dramatic slowdown in the installation of cables to pass homes, as the focus is rather on the number of homes connected. Okay, looking at installation options, there are various techniques being employed. For example, microblown cable technology, which is very popular due to its obvious advantages. Operators that already have underground infrastructure make use of this to deploy microducts, where the microblown cables can be installed as and when needed. Unfortunately, underground infrastructure involves a huge civils cost component and is, of course, slow to put in place. You have more sophisticated methods like micro-trenching, which is used in areas or communities where they are sensitive to appearance. But aerial installation, however, seems to be the obvious choice in a very competitive environment where speed is critical. The current aerial infrastructure distributing copper lines in a lot of areas is a very attractive option for quick fiber installation. So you have these telephone poles typically running in between houses in residential areas, and of course you have drop points already available at regular intervals. So it is quite easy to deploy fiber cables on the same infrastructure. There are some installation realities. Installation teams, when moving in, try to move as fast as possible. They may encounter various challenges. For example, property owners are not always available to allow access, and in some cases disallow the cutting back of garden trees and so on that would otherwise provide a more straightforward routing for the cable. However, installation teams even climb over boundary walls and do whatever is necessary to get the cables in. The photographs show a typical sequence of events. Photograph 1 shows a cable being routed in between trees. Number 2 shows a temporary coil of cable left hanging in a tree. You can also see the old copper infrastructure that is visible there. In number 3, the cable is now tensioned up, and at that point a drop box was also installed. But it could actually take months afterwards before the actual drop cable is deployed into the house. So the initial rush to get the cables in was purely the operator's initiative to claim the area. So we've also seen cases where there's an excessive time lapse in between installation steps. For example, leaving a coiled up cable in an uncontrolled manner for long periods, which increase exposure to damage. And now skill levels of installation teams probably not always as high as one would desire. As the photograph on the left shows, poor application of a dead-end clamp. Bottom right shows that fibers are not properly organized in a fiber organizer and probably exceeding bend requirements. So the final installation may therefore not always be completed perfectly, and returning to site may be required to remedy problems. So after all of that, we decided that things had to change. We targeted 2 key elements in order to improve the situation. Firstly, it was decided to reduce the cable size and weight, and secondly, to enhance the bend tolerance of the fibers. So choosing a 200 micron diameter fiber that meets the bend requirements of ITU-T G.657.A1 became the obvious choice. Such a fiber provides the opportunity for higher fiber counts as well as more densely packed cables. One would expect the larger coating of conventional fibers to have more cushioning to external stresses, and the reduced coating of a smaller fiber, like the 200 micron one, to be more susceptible to forces being transmitted to the glass, especially in densely packed cables. However, the use of bend-resistant technology and advanced glass coating design makes the 200 micron fiber absolutely viable. Now, cable designs in this study have a reasonable strain-free window, and the packing density is therefore not a concern. Therefore, the bend tolerance of the 200 micron fiber can be fully exploited by allowing smaller and more visually unobtrusive closures to be introduced into the network. And of course, the 9.2 micron mode field diameter is also fully back compatible with legacy G.652.D fibers that's already in the network. Unlike microblown type cables where the packing density of fibers in a loose tube is exploited to the fullest, ADSS cables are designed to decouple fiber stresses from other cable materials. So it is necessary for fibers in an ADSS cable to have sufficient strain-free, as such cables are self-supporting and continuously exposed to tensile stresses when in service. In contrast to conventional cables incorporating 245 micron fibers, we can now design smaller loose tubes with the 200 micron fiber and still maintain a sufficient strain-free window. For ADSS cables, we typically aim for an effective fiber overlength in the cable to be between 0.4 and 0.6%, and we have managed to maintain this in the design of the new cables. The equations you see on the screen there is from the customer specification and requires that we calculate the tension under normal and worst case conditions. So a wind loading of 125 kilometers per hour or 78 miles per hour is considered to be the worst case condition. Due to South African weather conditions, ice loadings are not considered. Now, having sufficient strength members and a suitable strain-free window in the cable is then confirmed by the tensile test. So this slide shows a physical comparison of the new cables versus the conventional cables. We can see that the range is now extended to 288 fibers. If we look at a fiber density ratio, then we see that the new cables are on average 48% higher. The 288 fiber cable actually doubles up when compared with the 144 fiber conventional cable. This is also evident in the scale drawings there. Of course, the double layer construction do assist in this. The new cables are approximately 18% smaller in diameter and lighter by up to 35%. So the new cables being smaller and lighter is easier to install and can easily be co-located with other cables already on the wooden telephone poles. By installing the smaller and lighter cables at the top, one will ensure that there is no interference or clashing with the other cables. Because the graph there shows that for the same fiber count cable, the new cables operate at substantially lower tensions. Right, we've carried out type testing on the cables, and I'll be showing you the results of the 288 fiber cable incorporating the 200 micron fibers. Now, the test requirements and so on for the new cables are the same as for the conventional cables. Key network operators over here have their own specifications. However, these are generally based on the IEC 60794 series of specifications. Operators, however, do tend to tighten up on certain requirements depending on their needs and experiences in the field. The graph showing the tensile result there, which shows that the fiber strain for the fibers in both loose tube layers were well within the 0.2% requirement at worst case conditions. And also the range of strain-free operation for normal conditions is clearly evident. The cable also performed very well during the prescribed other mechanical tests, as can be seen in the table, and I'm referring to crash, impact, torsion, and bend tests. Okay, environmental tests. The key environmental tests for an ADSS cable are considered to be temperature cycling and a long-term creep test. Now, temperature cycling comprised of 4 24-hour cycles. The temperature profile is visible there. It varies between minus 10 degrees Celsius and plus 70 degrees Celsius. The attenuation changes were actually very small at 1310 and 1550 during this test. During the long-term creep test, the actual hardware or cable clamp is used in conjunction with the cable. The load to be applied is calculated at midway between everyday stress and the maximum applied tension. The actual installation is simulated by hanging weights over a pulley, which is attached to the cable and clamp, as shown in the structure, bottom photograph. In this test, we are looking for the cable elongation to stabilize early on, typically within the first 2 to 3 days. And we also check to ensure that there is no movement between cable and clamp over this period. The cable met the requirement quite comfortably. Hardware compatibility. This is actually a company internal test. We normally refer to this test as the hot box test. The test originated many years ago when we started with ADSS cables. There were problems back then with slippages, especially in warmer parts of the country where day temperatures often exceed 40 degrees Celsius and sometimes peak at temperatures over 50 degrees Celsius. So we are still doing this test today, and you can see the setup there. There's heater elements in the box, and the cable and its associated hardware is soaked at 60 degrees Celsius for 2 hours, after which a load of 3 times the maximum applied tension is applied for 10 minutes. And at the end, of course, we expect not to see any movement between cable and clamp Now, this test is becoming challenging lately as operators are looking at optimizing hardware. For example, they're looking at shortening the clamps as it's easier to apply. And because of this, we may have to review this test requirement. Okay, as discussed earlier, the conditions can be challenging. Skill levels of installation teams perhaps not always as desired, although I do admit that things are improving a lot lately because of more and more training that was introduced. We're looking at a situation where closures can be much smaller than usual, and there's a lot of handling of the cable due to mid-span breakout of loose tubes, and where fibers need to be taken out at regular intervals for the drops. Now, typically, the span distances here can be even less than 60 meters. So with all of this going on, it is important to have a successful first-time installation. Recently, we've seen some unconventional methods. If you look at the pictures there, this is a drop cable that was actually attached to an ADSS cable in mid-span instead of planting another telephone pole. So you have additional load conditions to the ADSS cable, which is not necessarily accounted for. Fortunately, making use of a design that's having a reasonable strain-free window, such conditions can be tolerated somewhat. Okay, we also did some loose tube kink tests at different temperatures and at loop diameters smaller than the usual 60 millimeters to simulate the more severe conditions. The storing of loose tubes in closures is a manual process that requires exposure and mid-span breakout of loose tubes. Approximately 1.8 meter of loose tubes will be coiled over 3 times and stored into the storage cavity of a closure. It is normally also at this point where the necessary fibers are exposed for connection to the drop cable. The table shows the enhanced storage capacity for the new cables due to their smaller buffer tubes, of course. One is able to move one cable size up without needing more space in a closure. Okay, so we find the new cables to be much more tolerant to the smaller connectivity plant and incidents where buffer tubes and fibers are coiled in diameter smaller than the usual 60 millimeters. There's certainly less rework and many more successful first-time installations. When looking at the spectral attenuation curves, we see the bend-tolerant property of the fibers in the new cables also to provide a future upgrade path for higher speed transmission relying on longer wavelength operation. The spectral attenuation curves here represent 1 kilometer fiber attenuations and 10 by 30 millimeter diameter bends for different fiber types. And we can see the difference between the standard G.652.D fiber and the 200 micron fiber, incorporating the bend tolerance of a G.657.A1 fiber. So in conclusion, we have a new range of cables, which is also a wider range of ADSS cables, which provides for more efficient overhead installation. The enhanced macro-bend performance of the optical fibers and smaller buffer tubes provides opportunities such as reducing the size of connectivity plant. Having less rework with lower skilled installation teams, and of course it allows for a future upgrade path for higher transmission speeds relying on longer wavelengths. So I guess we can say that we have achieved our goal of coming up with a new range of ADSS cables that counter the challenges we are dealing with when deploying conventional cables.
Very good. Thank you, Paul. At this time, we will ask as many questions from the attendees as time permits. starting with this first question. How do you see the infrastructure deployment occurring in South Africa for rural or farm areas? Is there any government support to make this happen using the 200-micron fiber cables?
Yes, the rural and farm areas, of course, is a bit problematic. So there's still a lot of radio systems. The cost is very high to get fiber in there, so that is problematic. Going back to the country map that I've shown, you can see the concentration of fiber deployment is more in the main centers. Obviously, it's a case of where people already have broadband. A lot of people have ADSL from the copper infrastructure, and I think the operators are going after those areas first, where they can get a return on the investment.
Okay, thank you. Next question. With reduced diameter 200-micron cables, are there any concerns with mechanical or long-term attenuation problems due to rodent or animal attacks or any other environmental hazards?
We don't really see on aerial cables too many rodent attacks in South Africa. It's more where the cables come down from the telephone poles and into the manholes. That's where things can be problematic. But what people normally do is they have a protective sleeve running down the telephone poles that protects the cables at that point. So it's not really problematic. It's more in the case of underground cables where we see rodent attacks. So I guess we're quite fortunate from that point of view. There's so many kinds of rodent species. In the KwaZulu-Natal area, you get the sugarcane rats. They can become rather big and problematic, though.
Okay, thank you. Next question. How long can the fiber cables be deployed between splice links?
Between splice links? Well, in general, the standard cable length being produced is, in a lot of cases, are 4 kilometers. We do, however, produce certain cables up to even 10 kilometers. So I guess depending on the installation techniques, one can fully utilize the cable length, the full cable length, before you need to splice up again.
Okay, thank you very much. Paul, at this point, I see no further questions, so I'm going to go ahead and thank you very much for presenting this interesting and important topic today. Please note the contact points being shown should you wish to contact Paul after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The next webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, June 15th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 66 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 14th through Wednesday, October 17th, 2018, at the Rhode Island Convention Center in Providence, Rhode Island, USA. In addition, the third annual UL and IWCS China Cable and Connectivity Symposium will take place on Tuesday, March 26th through Thursday, March 28th, 2019 at the Shanghai International Convention Center in Pudong, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.